Good morning, student. Namaskaram. Today we are going to discuss 12th physics topic, chapter name ray optics, topic name Cartesian sign convention. Okay, which is the fundamental concept in optics. This convention help us to determine the signs of various parameters such as object distance, image distance, and focal length when dealing with the mirror and lenses. Okay. Okay. So first of all, let me draw one diagram, which is the for discuss that uh, Cartesian sign conventions rules. Okay. So this is mirror. Okay, spherical mirror. This is spherical mirror, and this is the principal axis. Already you know that. Yeah, this is principal axis. This is incident ray, incident light ray. So incident ray. So here object is there. Yes. So object is there. So heights measured upwards. So here height measured upwards because object placed on the principal axis in upward direction. So positive. And suppose we need to measure the height downwards. In that case, this is negative. Height measure downwards negative. So incident ray passing like this, and if the distances measured against the incident ray direction, so distance measured against the incident direction are called negative or denoted as negative. And the distances measured in the direction of incident ray is positive. Clear? So this is a basic sign convention. So I will teach you in detail. Okay. So distances measured along the direction of the incident light ray are called positive. So that means, so incident objects there, incident ray is there, incident ray coming like this, and the distances we need to measure in that along the direction of incident ray. So in that case, we need to put positive. So that directions are considered as positive. Suppose distances measured against the direction of incident light ray are negative. Clear? Okay. So height above the principal axis are positive. Height measured below the principal axis are negative. Clear? This is the principal axis. Suppose we have to measure one height from this upwards. So we need to put positive sign. For the downwards, we need to put a negative sign. And then object distance and image distance. Object are there. Okay. The object is that there. So always it is negative because object is always placed in front of the mirror. So we have to measure distance from this position. This position is called P. Okay. All the distance measured from the pole of the spherical mirror. So pole is the reference point. Pole is the origin point. Pole is the starting point. Okay. So all distances measured from the pole of the spherical mirror. Clear? Okay. So incident ray coming from this object. So we need to measure that object distance between pole to that position. So we need to measure distance from this to this. So incident ray against passing. So that is negative. So object distance u. Okay, this is a object distance. U is negative. Object distance means here to here. This is u. So u negative. For that image distance, uh, it will change. Okay. So let's start with the object distance, which is denoted by u. The object distance is the distance between the object and the pole of the mirror. According to Cartesian sun convention, if the object is in front of the mirror, the object distance is front of the mirror. Okay, front of the mirror, object distance. We need to measure the from this to position this position. So negative. Okay. Suppose behind the mirror, object distance u is positive. Okay, right. So let's we have the image distance. So image may be formed at front of the mirror or behind the mirror by the convex mirror and concave mirror. Okay. So which is denoted as V. So V. Okay. This is image distance. So image distance is the distance between the image and the pole of the mirror. Okay. Distance between the pole of the mirror, pole and the image. Clear? So if the image, if the image distance, which is measured as V, suppose if the image is a real image, there are two type of image form. Okay. Another one is virtual image. Image distance, real image and a virtual image. So image is a V for real image negative. For virtual image positive. Because real image formed in front of the mirror. Okay. So suppose a mirror in front of the mirror means here. So in front of the mirror. So we have to find the distance between pole to that image. So against the incident ray, so negative. So real images formed in front of the mirror. So we have to put image distance V as negative. For virtual image, that image formed behind the mirror. So we measured the image distance along that incident ray direction. So that's why we are putting plus positive sign for that virtual image. That is Image formed behind the mirror. It is clear? Okay. Then next, focal length. Already we know that for that we have two type of spherical mirror. One is concave and another one convex. So focal length. Already you know that the distance between the principal focus and the pole. So focal length positive for convex mirror. Okay. Negative for concave mirrors. So focal length. Okay. So distance between, because for the concave mirror, the uh, light rays are incident on the spherical mirror and converge at the focus. The focus formed in front of the mirror. So it is negative for concave mirror. For convex mirror, focus behind the mirror. So it is for convex mirror, it is positive. Okay. Then another one, object height. Already I told you that is object height is positive because object always placed on that principal axis above that principal axis. Okay, so object height is always as positive. Image height. Image height. Positive for upright image. Upright images. Negative for inverted images. Okay. So inverted and upright, already you know that upright and inverted. Inverted means suppose your image, sorry, your like one object placed on the mirror, image formed inwardly, reciprocal to that object is called as inverted image. Yes. So positive for upright image, inverted reciprocal to the object, that is image height negative. Because already I told you object is above to the principal axis, inverted means reciprocal, so downward to the principal axis, so negative. For upright images, image also in front of the mirror in the upright direction, so which is positive. So these are all sign conversion. Clear? Okay. So object distance, image distance, focal length. Okay. And for example, to illustrate this convention, let us consider a few example. A concave mirror, which is concave mirror. Yeah. Focal length positive 10 centimeter. It has an object here. So object, real object placed 20 centimeter from in front of the mirror. Okay. In front of the mirror, concave mirror. So object distance minus 20. Yeah. So minus 20. Because from pole to this object. Clear? For convex mirror. For convex mirror, let me write convex mirror. So this is This is example for convex mirror. So here object, so positive. And this is pole, here focus. So focal length. So here, so this is also positive. Yes. So focal length of convex mirror always positive. Is it clear? Okay. So these are all belongs to sign convention. Thank you. So next we are going to discuss another one concept, that is critical angle and then total internal reflection. So critical angle, first one. Okay. So critical angle, when a ray, that is light ray, passing from denser medium to, this is denser medium, this is a rarer medium. So when a light ray is passing from denser medium to a rarer medium, the angle of incidence in the denser medium, for which the angle of refraction becomes 90 degree in rarer medium, is called uh, critical angle. Okay. So like this is the denser medium. So this is normal. Okay. So between normal and the incident ray, you know that I or I1. Okay. Right. So incident angle. This is refraction, refracted ray. Yeah. So there is an angle between a normal to refracted angle, that is angle of refraction. So R1. Here I1, this is R1. Okay. This is denser medium, this is rarer medium. The rarer medium means you can take air or vacuum. Denser means you can take glass or water. So next step, you increases this light ray, that is angle of light ray from this position to this position, you increases the angle of incidence. Yeah. So that means I2. So now I2. So in that case, this also will change. Yes, this is R2, which is different from the previous one. And then again, you increases the incident angle again. Finally, refracted ray or refraction angle becomes 90 degree. So which traces the boundary. Okay, which traces the boundary. So in that case, the angle of incidence becomes a critical angle, C. So refracted ray traces the boundary between the two surfaces in one angle of incident angle, that is incident ray. Okay. When light rays passing from the denser medium to rarer medium, the angle of incidence in denser medium, for which the angle of refraction becomes 90 degree. So whenever angle of refraction becomes 90 degree in the rarer medium, for which for one particular angle of incidence, that angle called as critical angle. Clear? So equation for critical angle in your book, N21, 1 by sine IC. So N21 means Raphite index of the denser medium with respect to rarer medium. Because already we know that for that air medium, Raphite index is 1. So for the denser medium, there will be some Raphite index. So N21 means denser medium with respect to second medium with respect to first medium. So denser medium with respect to rarer medium, Raphite index. N means Raphite index. 1 by sine IC. This is a formula for critical angle. Clear? I will show you a simulation for this critical angle. So here you can see one simulation. Okay. So here downwards denser material, denser medium, upwards air medium, Raphite index n is equal to 1. Already told you. Index of refraction means for this denser medium, there is a Raphite index. So 1.52, we can change water, glass, whatever may be. Okay. So now incident first step. So incident ray. So here 28 or 30, 33.33, 33.3 degree, which is a angle of incidence. Angular reflection, that is in red color. So that is also will same to the incident angle. So angular reflection also 33.3 according to the Snell law. Already we know that. So angular refraction from that normal to refracted angle, refracted ray. So gamma, which is equal to 56.56 degree. Okay. Suppose the angle of incidence I gradually increases. You can see that, or rapidly increases also. Okay. So 60, 60, 68, 70. So angle of incidence increases, angular refraction also increases. Refraction also increases. Okay. So at particular, okay, once again, okay. So at a certain stage, R becomes 90 degree. So 90 degree. Okay. R becomes 90 degree and the refracted ray will be grazing the boundary. Okay. So uh, refracted ray will be grazing the boundary. So the angle of incidence in the denser medium for which the angular refraction is 90 degree or the refracted ray grazes a boundary between the two media is called critical angle. So now incident angle is the 41.3 degree, which is the critical angle for this case. Okay. You can see for 86 and 90. So this is critical angle. Clear? Okay. Next concept is total internal reflection. Total internal reflection. Okay. This is another one concept. So total internal reflection, TIR. When a light ray passing from the denser to rarer medium, if the angle of incidence is greater than its critical angle, already I'm showing one simulation that is in that case I is something 48 point something something. Okay, so in that case we get a critical angle that means refracted ray grazes the boundary that is 90 degree between the normal. Okay, this is R. So this is something, for example, 48.3 degree. Okay, this is I. So when a light ray is passing from the denser medium to rarer medium, if the angle of incidence is greater than the um, critical angle, that is I is greater than IC. it gets reflected same denser medium. So it reflected same into denser medium, same medium without any refraction. So there will be no refraction. So this phenomenon is called total interreflection. An optical fiber works on this principle of total interreflection. So in the optical fiber, signals are passing by the light signal. So communication, okay, communication channel. So in our communication channel, the signals are converted into electrical signal, which is passing through that fiber optic cable, like this by this principle. So whenever angle of incidence greater than the critical angle, it gets reflected into the same medium. That is called as total internal reflection. So here also, I am showing, I will show one simulation for that this concept. So, okay. So now you can see that for the denser medium, incident angle 40.61 and refracted 81.61 degree. So angular refraction. So I am increasing, okay, increasing. So in that case, all the lights ray reflected back to the same medium. There is no refraction because the angle of incidence is greater than the critical angle. So the entire light reflected back into that incident, sorry, denser medium, that is same medium. For the critical angle of incidence, already we know that angular refraction is 90 degree. I becomes IC. Clear? So angle of incidence become IC and angle of refraction 90 degree. From that, uh, we will discuss the sorry. Already I told you that is a formula for angle of sorry, critical angle. Yeah. So N21 is equal to sine IC. Yeah. Okay. So this is total internal reflection. The light ray reflected back into that same medium. So for the critical angle, I become angle of incidence becomes IC whenever the angular refraction becomes 90 degree with respect to normal or graces the boundary. That is in that case of critical angle. So after increasing that angle of incidence greater than the critical angle, all the light rays reflected back to the same medium without any deviation. So here you can see that is called total internal reflection. So clear? Okay. So today this topic over. We will discuss another one topic in next class. Thank you. Jai Bharat, Jai Hind, Jai Vidyashakti.